So we're looking at the one of our notes sheets that we started in the last couple days. This is page 10 in your binder, Electron Configurations Part 3, and we're going to be talking about valence electrons today. So we already got the definition down here. Valence electrons are electrons on the outermost or highest energy level. Okay. So what does that mean? Take a look at the at a sheet of paper here. We'll go ahead and draw out a picture. So looking at, for example, let's find, how about sodium? Sodium's electron configuration, if we use the periodic table. Okay, let's see if we can get all that in here. Okay, so sodium's electron configuration, we start off 1s, okay, 1s2. The third electron going to come in here at the second energy level of the s block, 2s2. Bring it over this way. Next electron, the fifth electron, is going to have to go into the p orbital. We're still at the second level, so 1, 2, okay, 2p, 6. Next, after the 10th electron, that 2p6 is all done, we see sodium right here. It's in the third row of the s block, and we only need one electron, 3s1. So looking at sodium, we've got at the first energy level, the second energy level, and then the third energy level. So obviously the third energy level is higher than anything else. So there's one electron there. Okay, one electron in the third energy level. That's what it would look like for an electron configuration for, let's say, drawing a Bohr model. This is what it would look like. We've got 11 protons from sodium. At the first energy level, we've got 2 electrons. So we can draw 1 and 2. The second energy level, we've got 2 and 6. So a total of 8. So there's 1, 2, 3, 4, 5, 6, 7, 8. And then we've got one more energy level, and that's the third energy level. So here, it's the furthest away from our nucleus. Okay, it's the third energy level, the furthest away. It's the outermost. That would be a valence electron. Okay, now why is that important? So that is important. We're going to get to that. The maximum number of valence electrons an atom can have is 8. Now we talked about noble gases having a full octet. Well, oct means 8. So here's noble gases again. They tend to be stable and unreactive because they have a full octet of 8 valence electrons. Okay, we'll see how that all works. Now, the big idea is that every atom wants to have 8 valence electrons. Okay, wants to have a full outer shell. Okay, so what they're going to do, they're going to add or remove electrons in order to mimic a noble gas. Noble gases are kind of like the best thing out there, so everything else wants to appear like a noble gas. They do not actually become noble gases because we're only changing electrons. You can't change the type of an atom if you just change the electrons. You can change an atom if you change the number of protons. Protons determine the atom. If all they're doing is moving electrons in and out, they don't change the identity of the atom at all. Okay? And all that. So, what are we going to do? We're going to compare the electron configurations of hydrogen, lithium, and sodium. Let's bring back our picture here. So we've already got sodium. Let's take a look at lithium, which is 1s2, 2s1. And if we were to draw a picture, it's got 3 protons. At the first energy level, it's got 2 electrons, 1, 2. At the second energy level, it's got 1 electron. For hydrogen, it's got just 1s1. So it's got 1 proton and 1 electron in its outermost energy level. Okay, so each of these 3 atoms, and they're all happening to be from the same group here, hydrogen, lithium, sodium, all from the same group. They all have the same number of valence electrons. Okay, and that number is, come back over here, 1 electron in their outermost energy level, so 1 valence electron. Now, what are they going to do here? They want to end up looking like a noble gas. So they want to have a full valence shell. Okay. For most atoms, that means 8. Okay. So for looking at sodium here, for it to have a full valence shell, it's only got 1 electron right now. So one thing it could do would be to add electrons to its valence shell, to its 3rd energy level, until it has 8 out there, which means it could gain 7 electrons. Well, that seems like a lot of work. What else could sodium do? If instead of gaining 7 electrons, sodium decided to get rid of its outermost electron, it's just going to drop that 3s, and instead now it's going to look like this: 11 protons with 2 electrons in the 1st energy level, and 2 plus 6, 1, 2, 3, 4, 5, 6, 7, 8. Now it's got 8 electrons in its new outermost energy level. The fact that it's dropped down 1 energy level from 3rd to 2nd doesn't matter. It is perfectly happy having 8 electrons in its outermost level. Okay, it's perfectly happy doing that. Doesn't matter that it had to drop. So if it gets rid of its 1 valence electron, all of a sudden now it has 2 plus 4 plus 6. Excuse me, 2 plus 2 plus 6 is 10. It has 10 valence electrons. Excuse me, not 10 valence electrons. Forget I just said that. It has 10 electrons, which makes it look like neon, which, what do you know, is a noble gas. So remember, these things are always trying to gain or lose electrons to make it themselves look like a noble gas. Okay? Now, here's the other question. We've got 11 protons, which are positive, and 10 electrons, which are negative. 1 more positive means that this thing is going to be overall with a positive charge. Okay? So, it is going to be much easier for this thing to lose 1 electron and end up looking like a noble gas. Lithium can do the same thing. If it gets rid of that outermost energy level, then it just looks like 1s2, which is a noble gas. 1s2 is the electron configuration for helium. Okay? Hydrogen's a bit of an interesting case. What it's just going to do is get rid of its only electron, and it's perfectly happy. The important thing is that every single one of those atoms is going to do the same thing. It's going to give up 1 electron. Okay? So, go back to our notes here. They're all going to lose 1 electron in order to become a stable atom with a charge of +1. If you lose an electron, you end up with a positive charge, because electrons are negatively charged. Okay, so let's go ahead and look at the rest of these, see how they all work out. Okay, the next question is beryllium and magnesium. So here's beryllium, 1s2, 2s2, magnesium, 1s2, 2s2, 2p6, 3s2. Okay, so what they're going to do, they've got 2 electrons on their outermost energy level. They can fix that either by gaining 6 or by losing 2, or by losing the 2 that they have. Whichever involves less motion of electrons, they're going to pick. It's a lot easier to lose 2 electrons than it is to gain 6. Okay? So they have 2 electrons in their outermost energy levels. They're going to lose those 2 to make themselves look like a noble gas. So both of them exactly 2 electrons. They've got 2 valence electrons. They're going to lose 2 of them to become a charge of now +2. Let's move on to finish up the bottom of this page. Okay, so we're going to figure out the electron configuration of sodium plus and magnesium 2 plus. Well, sodium plus we already figured out. It's got 11 electrons to start off with, and this positive charge means that it's already lost 1. So it's going to lose an electron and end up with 10. Magnesium starts off with 12 from the periodic table. The plus 2 means that it's lost 2, which means now it has 10 electrons. So, 10 electrons. 1, 2, 3, 4, 5, 6. Notice they're not pairing up yet. 7. That's Hund's rule. They're only going to pair up now. 8, 9, 10. 10 electrons. Magnesium 2 plus, also 10 electrons. 1, 2, 3, 4. Again, they don't pair up. 6, 7, 9, 10. Okay? Well, what do you know? 10 electrons. They both have 10 electrons. They both have the same electron configuration. And if we're quick, we notice that that 1s2, 2s2, 2p6 will get us all the way up to neon. Follow it. 1s2, 2s2, and 2p6. So both of these atoms are going to end up looking like neon. We're going to try this once more. Compare the electron configurations of boron and aluminum. I'm going to go ahead and just write these in right here. Boron is a 1s2, 2s2, 2p1. Aluminum, 1s2, 2s2, 2p6, 3s2, 3p1. The outermost energy levels, second for here, there's 2 and 1. Together makes 3. Aluminum, third energy level, 3s2, 3p1, a total of 3 electrons. Okay, 3 valence electrons. So once again, they can either gain 5 to have 8, or they can lose the 3 that they have. It's a lot easier to lose 3. So they're going to end up having a charge of plus 3. Now, let's take a look. We've already discovered sodium plus, magnesium 2 plus both have 10 electrons. Aluminum has 13, but aluminum 3 plus has lost 3. They've all got 10 electrons, so they all look like neon, which is a noble gas. Okay, isoelectronic. Iso means same, and obviously electronic is all about the electrons. Let's go back and take a look at some of the ones that won't be losing electrons. So we flip over. So we're going to compare the electron configurations of fluorine and chlorine. Okay, and we're going to go ahead and do this on this paper here. Okay, fluorine and chlorine. Here's fluorine, and it's going to look like 1s2, 2s2, 2p5. Here's chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. And we're going to go ahead and draw out fluorine, okay, what it looks like as a Bohr model. So fluorine has got 9 protons. It's got 2 electrons on the first energy level, and got 2 plus 5, 7 on the second energy level. So there's 1, 2, 3, 4, 5, 6, 7. It only needs 1 more to get 8 for its in its outer energy level. Same deal over here for chlorine. I'm not going to draw it out, but it's got 7 electrons at its third energy level. It only needs 1 more. So instead of getting rid of all 7 of these guys and starting over, it's very much easier for fluorine and for chlorine to just gain 1 electron. They've got 7 electrons in their outermost energy level, and so they are actually going to gain 1. Now, if it gains a negatively charged electron, it's going to have a charge of -1. Okay, move on to the next one. Oxygen, 1s2, 2s2, 2p4. Sulfur, it looks like neon with a 3s2, 3p4. Okay, let's go ahead through that one and just make sure that we're all comfortable on how to get that. Okay, I'm going to zoom out a little bit here so you can see the whole periodic table. Okay, so to get to sulfur, I'm going to go 1s, okay, over to 2, 2s, 2, 2p, and we can fit all 6 in there. We jump over here to the s block, that's 3s2, and then over to sulfur, 3p, 1, 2, 3, 4. Okay, zoom back in so we can see these a little bit easier.
That's too much. There we go.
Okay, so they both have 2s2, 2p4, that's 6 valence electrons, 3s2, 3p4, that's, again, 6 valence electrons. Okay, 6 valence electrons. So, they've each got 6 and 6. It's going to be a lot easier for them to not lose, to gain 2 electrons to get up to their 8. They're going to have a charge of -2. Okay? We're going to compare the electron configurations of nitrogen and phosphorus. I think we can take on our word right now that nitrogen, 1s2, 2s2, 2p3. Phosphorus is going to look the same, except it's all the way up at the third energy level, 1s2, 2s2, 2p6, 3s2, 3p3. It's got 5 electrons at that level, so 5 valence electrons, and it's going to gain 3 to have a charge of -3. Okay, fluorine starts off with 9, gains 1. Oxygen starts off with 8, gains 2. Nitrogen starts off with 7, gains 3. They all have 10 electrons, so they all look like neon. Here's the takeaway. We're going to complete the following chart. Well, all we need to do is go back and look at what we've done previously. Hydrogen, lithium, potassium, sodium, all that. We've already discovered they have 1 valence electron. And the oxidation state, this is the charge they want to have. The charge they want to have, okay, after they react to make sure that they have their noble gas thing going on. So what they're going to do is lose that 1 valence electron, which means they're going to end up with a +1. Beryllium, magnesium all have 2 valence electrons, which means they're going to lose them both. Boron and aluminum and all that have 3 valence electrons, so they're going to lose them. Carbon has 4. Now this is going to go either way. It can either lose all 4 or it can go up 4, which means it's going to be either + or -4 is the charge it's going to take when it's all done. We just did this one. Nitrogen is going to have a charge, is going to take a 5 valence electrons and have a charge of -3. Oxygen has 6 valence electrons, has a charge of -2 when it's reacted. The halogens over here have 7 valence electrons, and once they've reacted, they're probably going to have a charge of -1. The noble gases are going to have 8 valence electrons, with the exception of helium. It's only got 2, but it's only got 2 because the first energy level is full, and it's okay. It's happy with that. They're all going to have 0 charges because they don't react. So, last little bit. The electron configuration of argon here. Argon has 18 electrons. We've already got 2, 4, 6, 8, 10 here. So here's 11, 12, 13, 14, 15, 16, 17, 18. Now here's what we need to consider. We've got 18 electrons. If this had an ion with a -1 charge, which means that to get to 18 electrons, it has already gained 1 electron. To get to 18 means it must have started with 17 electrons, means it must have started with 17 protons. With 17 protons, that must mean it's chlorine. If it's got a -2 charge, that means it's already gained 2 electrons to get to 18. If it gained 2 and is now at 18, it started with 16 electrons, or 16 protons, which is sulfur. Going the other way, if it's a +1 charge, that means it's lost 1 electron. It means it started out with 19. Okay, it means it started out with 19, and that's potassium. And if it started out, now it has a +2 charge to get to 18 electrons, it means it's lost 2 electrons. It is 20, which means the element is calcium.